It's not sad. They're not simple. It's better than some people's normal curves. Oh, yes. You want me to draw?
I can't draw.
No, that's okay. Neither can I today. You're welcome.
So can I use post-it notes? You just that's what I did for Scarlet Letter. When I finally I
Yeah.
do not remember what I wrote. What? How did I get? Oh, this was with 0.7.
I don't even have them anymore.
I think that's me too. I hope so. Do you want me to do the make a decision?
What? I'll look in a minute. I don't think so. All right, our parameter that we're interested in is the true proportions of free throws made. And then our null hypothesis is that p equals 0.7. The alternative is p is less than 0.7. So when we draw our normal curve, we put 0.7 at the center. And Lindsay found this standard deviation, bless you, by taking 0.7 times 0.3 divided by 50 and then square rooting it. That gave us our standard deviation of 0.0648. And then our p hat is 0.5 because 25 out of 50 is 0.5. So Lindsay put 0.5 on the normal curve. Sorry, words are eluding me today. And then we looked at less than. So she did normal CDF, really small number, 0.5, 0.7, 0.0645, and we get 0.001. And 0.001 is less than alpha, so we would say she is not a 70% free throw shooter. On a curve.
Is that supposed to be 199 to 0.8? What's that mean?
Right here, 0.5. Negative 1E99, and then 0.5, because that's the p-value we're interested in over here. Any other questions? All right, today we get to learn about type 1 and type 2 errors, and we also get to talk about the power of the test. So, is there a possibility that we may have made the wrong decision in the warm-up?
Yes.
Yeah. Brooke could be a 70% free throw shooter, right? So there is a possibility that we are wrong. Sorry, I'm going to flip back. So Lindsay said she's not a 70% free throw shooter. So in terms of how we write our conclusions, that would be rejecting H null and concluding the alternative, that Brooke is not that good. So we chose, based on our p-value, we chose, no, chose has one O, right?
Yes.
Ignore my double O. We chose to reject H null. But there is the possibility that H null is true. It's highly unlikely, but it is possible. So that's where we get errors. There are two types of errors, type 1 and type 2. So, excuse me, excuse me, maybe. Alright, so our picture is not really going to be a picture, it's just going to be a box. And we're going to have our box here. Going across the top is the truth. So there are two possible truths. The first one is that H null is true. The other possible truth is that HA is true. On the side, we have the decision we make based on our p-value. And there are two decisions we could make. We can fail to reject H null, and we can reject H null.
What's that thing? FTR.
Fail to reject.
Oh.
Yes, FTR, H null. So if H null is true, and we fail to reject H null, that means our test did a good job. If H null is true and we reject H null, that's known as a type 1 error. If the alternative is true and we reject the null, that's also a good job. If the alternative is true and we fail to reject the null, that's a type 2 error. So in words, A type 1 error is when H null is true. And we reject H null or accept the alternative. So we're picking the wrong truth. Type 2 error is when the alternative is true. And we fail to reject the null. Or we accept the null when it's not true. Yep.
What do we call it? False positive.
That would be nice and simple, wouldn't it? But we call them type 1 and type 2 errors in statistics. I didn't make the rules, I just teach them. Sorry. No. Learn type 1 and type 2. I know. Sorry. All right, and then the power of the test. Bummer.
Nice one.
Man, that sucks.
That top right box is the power of the test. So the power of our test is when the alternative is true, and we correctly reject the null. Correctly. I said correctly, and then I didn't put it. So my spacing is off, sorry. And we correctly reject each null. Or in other words, power tells us the ability of the test to correctly detect the alternative. May I move my paper up? Bless you. Alright, so we're going to look at an example and how type 1, type 2 errors can play into problems that we look at. So let's say that Childers, anybody take autos?
I was in that class first grade.
Yeah? So it used to say Mr. Pons, and then he retired and Childers took over, and I was too lazy to refix my typed up one, so I just whited out Pons and put Childers. So let's say Mr. Childers runs an auto parts store. Every Monday, a truck delivers him a large shipment of brake rotors. He will only accept the shipment if less than or equal to 9% of the rotors are rusty. If there are more than 9% that are rusty, he sends the shipment back to the manufacturer. He does not have time to investigate the whole shipment, so he takes a sample of 100 rotors, and he uses the following hypotheses. So the null hypothesis is that the proportion of rotors that are rusty is 9%. The alternative is that the proportion of rotors that are rusty is greater than 9%. So we're going to describe a type 1 error, and then we're going to state some consequences of making a type 1 error. So a type 1 error, H null is true. And we choose to reject H null. So in this context, if H null is true, 9% of the rotors are rusty. And if 9% of the rotors are rusty, it's a good shipment and Childers will accept it. If we reject H null, that means we're accepting the alternative as truth. And if we accept the alternative as truth, we think that more than 9% are rusty. And Childers is going to send it back if more than 9% are rusty. So what would be some consequences of that type 1 error? It really was a good shipment, 9% of the rotors are rusty, but based on the sample, Childers thinks more than 9% are rusty and he sends them back. Lindsay?
He returned a good shipment. That's the consequences of it, right?
That is one of the consequences, right? He's sending back good parts. Sorry, my big handwriting, I didn't leave much space. So consequences, he sends back good parts. Any other consequences you can think of?
You have to wait to get another shipment.
Yeah, so if he's out of rotors and then he sends back a good shipment, he could end up losing money because he doesn't have any on the shelf. There's one other that I thought of. It doesn't mean they're the only ones. Yeah.
He wouldn't have rotors for his class?
Well, I said he owned a store.
Well,
So he's losing money if he doesn't have rotors. Is the manufacturer going to be happy?
no.
No, he or she is going to be a little upset because Childers is saying, hey, you sent me bad parts, take them back, when in fact they were good parts. So he could make the manufacturer upset and ruin a business relationship. I'm sure there are others. These were just the 3 that I could think of when I was doing this problem ahead of time. And sorry, I ran out of page, so manufacturer looks really weird. Any questions? Alright, so that's a type 1 error in this situation and some possible consequences. So now we're going to do the same thing, but type 2. So type 2 is when the alternative is true. And we failed to reject the null. So if the alternative is true, more than 9% of rotors are rusty. really then it's a bad shipment of parts. If we fail to reject the null, that tells us that really we're accepting the null as true. And believe that 9% are rusty and keep them. So what are some possible consequences for a type 2 error? Keeping a bad shipment. What are some possible consequences?
You know, has bad parts.
Yeah, he's selling bad parts, right?
You get hurt.
Say that again, I'm sorry.
Hurt because of that part?
People could get hurt, yeah.
Is he basically losing money because he has to do another shipment?
I'm sorry, lose money, why?
Because he has to do another shipment.
Yeah, he's gotta, I would assume, get refunds, right? When people realize they're bad parts.
Yeah.
Sell bad parts, people could get hurt. Could lose money. Any other thoughts?
He has to kind of get sooner.
Yeah. I'm not gonna get into that much, like whether he could get a shipment sooner or not. We would hope he would request one, but what if the manufacturer only says Mondays only? All right, last part. Which type of error is more serious in this case and justify? This one, I'll be honest, is more of an opinion type question. There are reasons why both a type 1 error or a type 2 error is more serious. As long as you have a justification, you'll get credit. So, how many of you, show of hands, think type 1 is a more serious error? And how many of you think type 2? All right, Shania, why did you say type 1?
He could lose his deal with the manufacturer and then he wouldn't get any parts at all.
Okay, so making the manufacturer upset could ruin his business. Okay, somebody who raised their hand for type 2? Seth?
He could lose clients because they got hurt.
Yeah, so if people get hurt, you could lose customers. So like I said, both of them, there are reasons why. You could explain which one you think is more serious in this case, as long as you got the justification. So Shania said type 1. Lose relationship with manufacturer. I'm going to abbreviate manufacturer. And then Seth said type 2 because people could get hurt. Lose customers if people get hurt. Any questions? All right, you guys are gonna flip the paper over and you're gonna try one on your own. This time, the situation is a company that has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects an SRS of 15 new batteries and uses them continuously until they are completely drained. A significance test is performed using the hypotheses H0 that the mean battery life length is 30 hours, and the alternative that the mean battery life length is greater than 30 hours. Mu represents the true mean lifetime of the new deluxe AAA batteries. We got a p-value of 0.0276. I want you to describe a type 1 error in the setting, type 2 error in the setting, and then give me a reason why you think type 1 or type 2 is more serious. Yeah, so H0 is true. Their mean lifetime is 30 hours. But we accept the alternative is true, so we think they last longer than they actually do. I'll be right there. I'll be right there.
It says it's regular batteries.
So if they think
What?
H0
It
is
says
true,
it's regular
they're not
batteries.
mass produce numbers.
Technically, one of them
Cost.
Yes.
So if they last longer than 30
So,
hours, but
so
they
wouldn't number one
think
go
H0 is true,
home?
that they only last 30 hours, we're not
Wait, no.
Is that answer your question?
H0 is true. Yeah. Yeah, it's rejected. See? You see my problem?
Did you take this patent card so we can do that?
Not still party.
I got a pencil. I got a pencil if you need, Caleb. Really?
We should
to get us started with number 1.
Is your hair naturally curly?
If you had no hair, you
I would
had
just-
spider hair.
The four.
See, I had not straight, but it wasn't curly. And then I got a hairdo. And I got super tight legs. And then I had my first kid, and that was fun.
Does any of it continue?
Molly's got a stick straight hair. It's not fair. And she's got like 27 colors in her hair. And she has a natural one, like blonde right there, super blonde. I'm like, it's not fair, girl.
It's not fair.
And then Henry's hair is exactly like Belle's. Exactly. Except for the color, but the way it grows.
Like the
how
bulk,
thick it is.
the bulk.
Yeah,
Yeah.
it just grows, they both grow. It's very funny.
Huh?
So expensive. So cute. Cutest one. Expensive. And I was like, oh my gosh. His little pig could do all this for a long time. Yeah.
And I'm gonna scan you number 3 now. That Emma's got matching shoes.
Oh my god. That's great. I don't say
Alright, so type 1 error, H null is true, the batteries only last 30 hours. We reject the null and accept the alternative, so we think they last longer than 30 hours. So we're really keeping bad batteries or batteries that aren't any better than the originals. Type 2, HA is true, the batteries last more than 30 hours, but we fail to reject the null and accept the alternative and accept the null, and think that they last 30 hours. So we were making better batteries, but we don't think they're really better, so we don't make them. Which error is more serious? I'm going to put type 1 because they are spending more money since they think the batteries last longer when they don't. Questions? Alright, now we're going to get into the probability of a type 1 error and how to find the power of our test. So we're going to go back to the warm-up idea that Brooke is a 70% free throw shooter. We want to figure out what values of p hat are going to lead us to reject the null and fail to reject the null. We're going to use an alpha level of 0.05. So we're going to draw our normal curve. We always assume the null is true, so I guess we should rewrite those from the warm-up. H null was that Brooke is a 70% free throw shooter. HA was that she's less than a 70% free throw shooter. We assume the null is true, so this picture is assuming HO is true. And we're going to find the p hat that's going to tell us to reject the null or fail to reject the null. And let's see, Lindsay even found our standard deviation. So back on the warm-up, standard deviation was 0.0648. So we have 0.7 at the center. We're working with an alpha of 0.05. So we want to find the p hat that's going to give us a p-value of 0.05 or less. So do you have a question, Seth? Or were you just stretching? Okay. I just saw your arm out of the corner of my eye and I thought, oh no, sorry. All right, so we're going to find an alpha level of 0.05, a p-value, an area under the curve, right? So back here, we had a specific p hat. It was 0.5 because Brooke made 25 out of 50. And then we found the area under the curve. It gave us 0.001. This time we have the area under the curve, 0.05, and we want to find the p hat that's going to give us that cutoff value of 0.05. So we know this area under the curve is 0.05 or 5%. And this pen is dying on me. Now, if we get a p-value that's less than alpha, we're going to reject H null. So anything to the left of that p-value tells us we're going to reject H null. And then anything over here is going to tell us to fail to reject H null. So any p-value to the right of that pink line tells us to fail to reject H null.
What about if it was what if she was like more than the 0.7 free throw, but she's going to go really be at 0.7?
Well, our alternative is less than. You're thinking about if it was greater than or not equal to. But for now, we're just working with the alternative that she's less than.
Then why is the H null and an error?
because she just claims to be a 70% free throw shooter, not 70% or better at shooting free
But
throws.
she'd also reject it if it's more than.
That would be if it was not equal to, but we're strictly saying less than. All right, so how do we find this p hat right here at this line? What calculator function? If I know the area under the curve, I use inverse norm. And our area is 0.05. Our mean is 0.7. And our standard deviation is 0.0648. So, second bars, number 3, we want 0.05 for the area, 0.7 for the mean, and 0.0648 for our standard deviation. And we get 0.593. So this right here is a p hat that is equal to 0.593. So if we get a p hat that is less than 0.593, we're going to reject the null. If we get a p hat that is greater than or equal to 0.593, we're going to fail to reject the null. That pen is dying on me. Let's use this one. Now, a type 1 error is when the null is true and we reject H null. So if our null is true, that Brooke is a 70% free throw shooter, and we reject H null, we get a p hat less than 0.593. How often is that going to happen? What's the probability that we get a type 1 error? 5%. So the probability that we get a type 1 error is 0.05. And 0.05 came from where? Alpha. Came from alpha. So probability that we get a type 1 error, excuse me, is equal to whatever your alpha level is. We tend to use 0.05, but sometimes alpha can change. So whatever your alpha is the probability you're going to make a type 1 error. Reject the null when the null is true. Questions? All right, we're going to look at a different example. So our alternative says that p is less than 0.7, but we're going to consider a specific alternative that p is 0.5. And we're going to say if that alternative is true, will we make the right decision? So we're going to figure out the power of our test when the alternative is true and we correctly identify the alternative. So for this picture, we're still working with a normal curve. but we're going to assume that the alternative is true. So 0.5 is going to be at my center. HA is true. And if HA is true, that's going to change my standard deviation, right? It's going to be 0.5 times 0.5 divided by 50 and then square rooted. So this time we have 0.071 if I round for our standard deviation. Five's at the middle. Everybody good so far? Now, from the previous example, we know that if p hat is less than 0.593, we're going to reject our null. Or if p hat is greater than or equal to 0.593, then we fail to reject the null. So 0.593, we're going to say it's going to be like here-ish. Anything less than 0.593, we're going to reject the null. So anything to the left, we're rejecting the null. And then anything to the right, we would fail to reject. And I'm going to change colors, sorry. Over here, we're going to fail to reject H null. Now, we're looking at figuring out the power of our test. So the alternative is true, and we correctly identify that. So if the alternative is true, do we want to reject or fail to reject the null? We want to reject. If the alternative is true, we want to reject the null. So we want to find the area under this curve. And what calculator function is going to help me find that area? This time I don't know the area. I want to find the area, so what's that calculator function? Normal CDF. And our lower bound is going to be a really small number. So -1e99. The upper bound is that p hat of 0.593 that tells us when to reject or fail to reject. Our mean, because we assumed the alternative was true, is 0.5, and our standard deviation was 0.071. Second bar is number 2. 0.593, 0.5, and 0.071. So I get 0.905 if I round. And what that tells us is that 90.5% of the time, if the alternative is true, we will correctly identify that the alternative is true. So we assumed the alternative was true. We found the probability, we reject the null. what if the alternative is true and we fail to reject the null? What is that called? Type 2 error. Thank you, Seth. So the area over here would give us the probability we make a type 2 error. What's the relationship between this area and this area? They add to 1, or in probability terms, they're complements of each other, right? If I subtract this from 1, I'm going to get this area. So the power of our test is also found using 1 minus the probability we make a type 2 error. Sorry, my paper moved on its own. Yes.
How would you do this if HA didn't like equal something specific?
If I want you to find the power of the test, I will give you a specific alternative. Speaking of that, this box here, you can bet those are going to be 2 of the short answer questions on your test for this chapter. I'll give you a null and an alternative. I'll ask you to find the probability of a type 1 error and draw a picture showing why. And then I'll give you a specific alternative and ask you to find the power and the probability of a type 2 error. So star this, something, I don't know. Take a picture, but I promise it'll be 2 of the short answer questions. And the pictures are important. You won't get full credit if you don't have the pictures. Everybody good if we flip? Alright, so this time we're going to look at the same type of idea, but we're going to look at one of those special computer programming things. So the national mean score on the ACT is 18.6 with a standard deviation of 3.2. We believe students at North have a higher mean. So to find out, we take a random sample of 8 students and find their average. We're going to use an alpha level of 0.05 for our significance test. So the null hypothesis is that the mean is 18.6. That's the claim from all the data for all the people who take the ACTs nationwide. The alternative, we think that students at North have a higher mean, so our alternative is that mu is greater than 18.6. What's our sample size going to be? 8. So n is 8. What's sigma? .2 tells us right up here. Standard deviation of 3.2, and then what's our alpha level going to be? 0.05. So let's say that North actually has a mean ACT score of 21. In other words, we could say that the alternative is that mu equals 21. What's the power of our test? So I'm sure it's logged me out, but I'm going to switch over to an applet so that we can play around with that. Of course, it did log me out. Give me a second to log back in. Oh. Say that again? Oh, please. Nolan can wake up and get over it. Come on, Nolan.
I'm so tired.
It's Monday. You should be rested. All right. So here's my little applet. Our null hypothesis is that the mean is 18.6. Our alternative is that the mean is greater than that. It'll update in a minute. Standard deviation was 3.2. Our sample size was 8. And then our alternative was that mu equals 21. And it tells us our powers. So it did what we did on the previous page. It found an X bar so that we know when to reject H null and fail to reject H null. And then it assumed the alternative is true. And it used that X bar from up here. I wish it would label it a little more clearly. It took that X bar from up there and said, okay, what is the power of the test that the alternative is true, and we correctly identify that. So we found that the power is 0.683. So I'm going to come back over to this one. I don't press buttons anymore. I just need to switch over here. So the power of our test was 0.683. How would I find that, let's see, where did it go? How would I find this X bar right here? Inverse norm. Let's switch back to the paper. So to find that X bar that tells us the cutoff, we would use inverse norm. What would our area be? 0.05. Now, yes and no. Here, it was less than, so 0.05 was to the left. Now we're looking at greater than, right? Our alternative is greater than, so we're looking at the 0.05 being on the right side of the curve. So we're looking at the 5% being there. Now, if you have one of those calculators that asks you about the tail, you can use 0.05 and tell it the tail's on the right. If you don't have one, what area should we use? 0.95. And then our mean was 18.6. And standard deviation. How do you find standard deviation of a mean? Sigma divided by the square root of n. So we would take 3.2 divided by the square root of 8. And that would give us our X bar that tells us when we're going to reject H null and fail to reject H null. And I did it earlier and I got 20.46. Does that match what you thought? Thanks, Isa. And then if we were to use that X bar right here, 20.46, upper bound, because we're looking at greater than this time, would be a really big number, 1E99. Mean of 21, standard deviation of whatever 3.2 divided by the square root of 8 is. That's how they get the power of our test, from taking normal CDF and we use that X bar, that cutoff value. We're looking at greater than, so this time our cutoff value is the lower bound, big number for the upper bound. Use the alternative that mu equals 21 for your mean. And then it would be 3.2 divided by the square root of 8 for your standard deviation. Now, you will need to be able to interpret power. Power just tells us the probability that we correctly identify the alternative. So if the alternative hypothesis that mu equals 21 is true, we will correctly detect HA or reject H null 68.3% of the time. And then the last little bit, suppose we want to improve the power of our test, so increase the probability that we correctly choose the alternative when the alternative is true. What do you think we should do to our sample size? Increase your sample size. It's always the answer. Anytime they say, what do you do to your sample size? Just say increase. What about the alpha level? Increase your alpha level. Because if we increase our alpha level, I'm going to flip back here. If we increase our alpha level, that's going to move this further towards the null, and then that's going to move it further away from the alternative, which is going to create a bigger area. And then what if we had a different alternative value? If you move your alternative further away from the null, it increases the power of your test. I don't know what's wrong with that desk. Oh, it squeaks? I don't know. You sat in it? That's what happened? Sorry. What did you want me to say?
Someone else sat in it.
Yeah.
No, you sat in it.
Let's see. Nobody sat in it last period. I'm sorry.